Welcome. In this lecture, we're going to talk about subsets, or what it means for a set to be contained inside of another set. This is one of these things that one very frequently actually has to prove, and so it's good to both know the formal definition, and then I'll actually explain how you would prove that one set is contained inside another, because it's just a technique that one needs to know. Okay, so suppose that we have we have two sets. So we have that S and T are both sets. So we have that S and T are sets. Then here's the definition. We're going to say that T is a subset of S of S. So, and then we have notation for that. So the notation is, oops, that should be an F, not an S. So of S. Okay, and the notation is that T is a subset of S. Okay, if and only if, so, and this is just kind of common logic notation. This is just if and only if. I use it in definitions. Some people don't, but I do, because definitions are actually an if and only if statement. It's more standard to write if. I really like this. Okay, so if and only if every element of T, so every, and then I'm going to write this because we're talking about something in T, every element of T, okay, is also an element of S, is also an element of S. Okay, so in other words, it means that if S is in T, then S also has to be in S. So S is also an element of S. Okay. So how to prove? So how do you prove that T is a subset of S? So how to prove? So you just want to take an arbitrary element of T. So take an arbitrary element. So this is like element of T. Of T, and prove that element is also in S, right? And prove that element is also in S. Okay, so you're showing that each element, right? And this is because, so how did I know that this was the method to prove this? Because this is an if-then statement, that if S is in T, then it's in S. Okay, how do you prove an if-then statement? You show that it's like for everything satisfying this, so it's like a for all, so you want to do an arbitrary element, and then you show that it satisfies this part. Okay, so that's what it means to be a subset. So let's look at a special example. Okay, we have that the empty set is actually a subset of S, so the empty set is actually going to be a subset of S, and this is going to hold, kind of unhappy with that marker, that is going to hold for each set S. Whoa, so much better. I bet you can see this one so much better. Okay, so for each set S, until it stops working also. Okay. And so, right, and the way that you would show that is if the empty set was not a subset, then it would contain some element that's not an element in S, but it doesn't contain any elements, so that can't happen. Okay, so that's just something to know, is that the empty set is actually a subset of everything. Okay, so this is just a way of containment, and this is how you prove it. It's good to actually know that because it is something that actually shows up a lot, that you have to prove that one thing is a subset of another. Particularly, as you'll see in the next lecture, because it's part of the definition of what it means for two sets to be equal. And there are a lot of times you're actually expected to show that two sets are equal. So I hope this made some sense, and I will see you in that next lecture.